picture of, oh, recording in progress, okay. To kind of give you the big picture of the field. And again, I cannot see the slides. Okay. But I'm very happy to go into more details during the questions. And I also put my email here because I'm always happy to discuss or debate or answer any other question by email. Okay, so first, a little bit of context. So yeah, I always like to give more context to the ideas that I'm going to present in my talk. So this talk is rooted into my final year dissertation, so third year dissertation that I did last year. And originally, this is a topic that I wanted to go for. So topological biosignature networks in exoplanetary atmospheres. Now, upon discussion with my supervisor, who is Professor Giovanna Tinetti at UCL, who I'm sure some of you will know, we decided to go for something much more general, much broader, that we entitled BioSignatures Past, Present, Future. So this talk is really about highlighting the insights that we can gain from adopting a much broader perspective on a field and on a particular topic. Okay, so the common word in both titles is biosignatures, which are the signs of life that we look for. And biosignatures are really critical in our search for life in the universe because they embody both what we look for, so our understanding of life, what it is, what it produces, how it can be recognized, but also how we look for it, so our research strategies and our investigation instrumentation that we choose to prioritize. So through this talk, I'm going to address 3 big points. So first, I'm going to describe the evolution of the field and what I call horizon extensions. Second, I will present the hierarchy of the field and what progress in the last decades or so has mainly consisted in. And finally, I will consider the complex accommodation of interdisciplinarity in biosignature science. Okay, so first things first, I really want to emphasize that wondering about our place in the universe and whether or not we're alone is really not recent. So here is a quote from Albertus Magnus in the 13th century, already talking about the desire of the human mind to wonder and to question whether there is one world or many. What is unique about the second half of the 20th century, though, is that these questions moved from the realm of philosophy to that of science, to that of something that we can scientifically investigate. So, questions like, are we alone in the universe? Is there life out there? Suddenly became, are there any habitable and inhabited worlds? And how could we tell? Okay, so first, a timeline of biosignature science. So here is my little timeline. So biosignature science was really born in 1965 with Lovelock and this great paper that I encourage you to read called A Physical Basis for Life Detection Experiments. And it was born with incentives to search for life on Mars. And what Lovelock suggests is to approach life in terms of its measurable properties and to search for phenomena that are inexplicably out of thermodynamic equilibrium. So this is really a concept that is key and that I will come back to. And from this point onwards, the story of biosignature science is really one of horizon extensions that broadened the investigation scenery and marked critical shifts in mindset and research strategies. So the first one occurred in 1995 with the discovery of the first exoplanet orbiting a main sequence star by Mayer and Kellers. So there were exoplanets that were discovered before, but they were orbiting pulsars, or they were confirmed a bit later. But the first exoplanet orbiting a main sequence star really suddenly brings up the idea about habitability around other stars. And so this really opened up astrobiology beyond the solar system. The second horizon extension occurred around 2010 with the launch of the Kepler Space Telescope. And Kepler brought the first exoplanet statistics, so the first demographic trends of the exoplanet landscape. And in my opinion, Kepler's revolution is threefold. So first, it showed us that most stars in our galaxy, and actually 90% of stars in our immediate galactic neighborhood, are very different from our sun. They are much smaller, much colder, and much more active stars that we call red dwarfs or M dwarfs. And second, most of the planets that Kepler discovered, so more than 2,000, and this trend still holds today, most planets are unlike anything we know in our solar system. They have no analog in our solar system. They are between the size of the Earth and Neptune, and they're often called, either super Earths or mini Neptunes, but the distinction is poorly understood. So it's really a planetary environment that we're not familiar with. And the third revolution is that from Kepler statistics, every star in our galaxy is expected to hold at least one exoplanet, and multi-planetary systems are expected to be quite common. So, there are 10 to the 11 stars in our galaxies. That leaves a lot of planets and a lot of possibilities for astrobiology. So Kepler really brought the paradigm at the time that was to search for our twins. So to search for the Earth's twin, the sun's twin, and in general, the solar system's twin. So that's where we are now. And today there are close to 5,000 exoplanets discovered. And I expect a third horizon extension to occur by 2030, and this time to bring the first insights and the first real statistics about exoplanetary environments. And we're already starting to get a glimpse of how diverse these atmospheres are by looking at hydrogen-dominated atmospheres on terrestrial planets, for example, or ocean worlds. And I think that this will bring the other paradigm that we're following at the moment, which is to search for Earth-like atmospheres. Okay, so we can see that the investigation scenery of astrobiology has really widely expanded over the last 50 years. So a natural question that arises then is, well, has the concept behind biosignatures changed as much? Has it co-evolved with this expansion of our astrobiological scenery? Okay, so to answer this question, first, we're going to look at the current status of biosignatures today. So here is a plot that kind of describes the current status. I'm not going to go into too much details here, but what I want to show you is that the current consensus is to divide biosignatures in three broad categories: so gaseous, surface, and temporal biosignatures. So gaseous biosignatures are the spectral features of volatile species in the atmospheres of exoplanets. So mostly we're talking about oxygen as a product of oxygenic photosynthesis, or ozone. And these are mainly investigated in the context of chemical disequilibrium. So for example, the main gaseous biosignature on Earth would be the disequilibrium between oxygen and methane in the atmosphere, so between oxidative and reducing species. Then we have surface biosignatures. The most studied one is the vegetation red edge. So that's a sharp absorption feature at around 700 nanometers or so from plants and trees on Earth, which are ubiquitous, basically from chlorophyll-bearing organisms on Earth. And finally, temporal biosignatures are not new concepts in themselves, but are just the temporal change of either gaseous or surface biosignatures. So, for example, the temporal change of CO2 in the atmosphere, or the seasonal variability of surface albedo. Now, a very important idea is that these three categories are by no means investigated on the same level. There is actually a very strong hierarchy in the field, and actually surface and temporal biosignatures remain very marginal considerations and beyond the capabilities of even the next generation observatories. So the focus of the field, both in terms of literature content and instrument prioritization, is within the spectroscopic study of atmospheric gases within the context of chemical disequilibrium. So in other words, 50 years later, the field is still focused very much on the same concept that Lovelock first introduced in his paper in 1965. Now, don't get me wrong, there has been some progress, of course, in 50 years. But so what has it consisted in? Okay, so the first thing to realize is that the list of potential mechanisms capable of generating false positives, so that is signals that we're going to interpret as coming from life, whereas they're actually produced abiotically, so not by biology. So this list of false positives is growing faster than the putative ways of detecting life. So, these questions like, can a dead planet fool us? And how do we work around limited data? These are becoming more and more challenging and more relevant to investigate in detail. And this emphasizes the growing need for contextualization and circumstantial validation of every signal. And a good example of that is oxygen, which is, still today considered the leading biosignature gas, the most robust one. Well, actually, a lot of studies have talked about the many abiotic ways of producing oxygen, even on a dead planet. So, for example, so oxygen photosynthesis, of course, but you could also have stellar activity. You could also produce oxygen through photochemistry on dead worlds, and also through ocean loss, even if the planet is not inhabited. And O2 is by no means the gas that has the most false positives. It is just the most studied one. So you can imagine for other gases. And the leading concept of disequilibrium chemistry has also been challenged. So, for example, if we look at prebiotic Earth, so the Earth before any life emerged, well, it was actually already characterized by a significant disequilibrium from the coexistence of volcanic outgassing and water vapor in the atmosphere. However, when chemotrophic life emerged, so very simple life, this disequilibrium mostly disappeared and was mostly destroyed. And it is only with the formation of a liquid water ocean and the appearance of oxygenic photosynthesis that the large biogenic disequilibrium that we know now on Earth appeared. And it's also important to realize that disequilibrium, this word, means very different things to very different scientists, and isn't very completely understood for basic environmental considerations like volcanism, stellar irradiation, atmospheric dynamics, and very often these are disequilibrium processes that are not taken into account in our models or in our simulations for simplification. So this is definitely something to keep in mind. And then within this contextualization, other things to consider are first the influence of the activity of M dwarfs. So how do M dwarfs and their activity reduce the prevalence of biosignature gases on exoplanets? Well, yes, but to what extent? This is still debated. And then, also what is the impact of tidal locking? So the fact that a planet, as it orbits its star, is only showing the same face to its star. So what are the consequences of that in terms of atmospheric mixing, in terms of habitability, in terms of high energy particle bombardment, for example? So these are really considerations that emphasize, again, our need for contextualization and circumstantial validation. And so, all this forces us to account for more and more parameters. So in our models first, and in our observations later. And this leads to a very complex and unprecedented network of uncertainty. As a result, most progress over the past decade or so has consisted in wrapping our leading concept of chemical disequilibrium in quantitative frameworks. The most favorite one in the literature today is the Bayesian frameworks. I don't know how familiar you are with that, but I put a very simplified form of the equation at the top. And what Bayesian statistics do is that they bring together first the detected signals that come out of our telescopes, the contextual evidence, so the stellar environment, the planetary environment, the planetary system context in general, They also unite our prior expectations about life and its origin. And finally, our knowledge of false positives to output a posterior probability of life being present from a given signal. And so what this framework provides is a very useful quantitative link between habitability and biosignatures. So between habitability and inhabitability, if that's a word. It's two concepts that were previously quite difficult to unite quantitatively. It also brings a focus on what is detectable. And in turn, this informs, for example, instrumental trade-offs. So is it better to, are we going to arrive at a better posterior probability if we obtain, a few spectra of golden targets, or if we obtain many more spectra of a large sample of targets? This is something that we also need to consider. And finally, a really great summary of Bayesian assessments is that what it does is that it combines current knowledge with observations to update our knowledge. And so basically what it means is that you update your confidence as all sorts of data accumulate. So whether it is a positive detection or negative detection, this always feeds your Bayesian framework so that your confidence is always upgraded. Okay, so while this is consistent, this wrapping within quantitative frameworks with more data being gathered, it does not constitute, and it should not be confused with conceptual innovation. Oh, I actually forgot. Sorry, I forgot to say one leap in the future that I'm making here is that I actually expect a second wrapping to come around with technological advancements. So that's artificial intelligence and machine learning. So why do I think that? Well, if you look at pure exoplanet science, you notice that in the literature, there is a burst of algorithmic and artificial intelligence tools. So especially machine learning and deep learning. So for example, when it comes to atmospheric retrievals, or exoplanet identification, or transit classification, or having a look at the interior structure. And what is interesting is that these machine learning and deep learning approaches have been installed to complement or fully replace the previous Bayesian frameworks that we used. That's why I think that it's probably what's going to happen to biosignature science in a few years' time. Okay, so now we're at it. So while this wrapping is consistent with more data being gathered, it does not constitute, and it should not be confused with conceptual innovation. The only occasion where it could compensate for this lack of conceptual innovation is in the context of the search for an anomaly. So as all sorts of data accumulate, you're going to try to create huge planetary and planetary system trends with all your data points. And therefore, it becomes much simpler to identify this particular point that's going to stand out of your data sample. And so the I'll know it when I'll see it kind of strategy, potentially meaning very, very different things to different scientists. This point stands out, something different is going up there. It could be life. So this is definitely an interesting compensation. Okay, so the goal of quantitative frameworks ultimately is to estimate the prevalence of life in the universe. But something important to realize is that the literature is often forgetful of long established favored directions or biases that are supposedly trivial, but important in the global picture of life that we're seeking to draw. So first of all, our focus on the Earth's O2 biosignature, when you look at it, well, this biosignature has only been detectable for the past 1/8 of its inhabited history. The Earth had too low levels in the Archean, too low levels of oxygen in the Archean, arguably too low levels to be detectable until about 0.75 billion years ago. So, 1/8 of its inhabited history, that's not much, and something definitely to keep in mind. And then our focus on looking for spectral features of gaseous species in the atmosphere means that we're only looking for complex life, especially when it comes to oxygen, because you may know that oxygen, when it arose on Earth, was actually responsible for one of the first and greatest mass extinctions on the planet. Prokaryotic life at the time, basically, not prokaryotic, but like more chemotrophic life, basically, was wiped out. It also brings a focus on extant life, so living life, and especially life requiring an atmosphere and interacting with it, right? And life producing a significant departure from equilibrium that we can ultimately recognize and detect in that atmosphere. So this means that there's an inherent bias towards surface life, right? So detecting life, for example, in the subsurface oceans of Enceladus or Europa would certainly affect our idea of the prevalence of life in the universe. But in the current state of our frameworks for biosignature science on exoplanets, we would have no means to account for it. And then finally, the most discussed biosignatures in the literature, which are oxygen, the Earth-like atmospheric disequilibrium, so methane and oxygen, and the vegetation red edge, all three of the signatures presuppose the advent of oxygenic photosynthesis, which is a metabolism that has been showed to have evolved only once on Earth. So, while all these biases are perfectly justifiable in terms of practicality, feasibility, and detectability, I think it's very important that we keep in mind what we're looking for and that we stay objective in the literature, basically. Okay, so what makes conceptual novelty and so hard, and why is it hard for us to distance ourselves from these biases? So the first hypothesis that we could make is, is life in our way? So you might know that you might not know actually, that I was surprised by this. There are more than 100 definitions of life in the literature, alongside many tries to analyze them epistemologically. And NASA's definition actually describes life as a self-sustained chemical system capable of Darwinian evolution. This is the definition that you will see the most in the literature. However, it has been criticized a lot for not being operational, so not producing testable hypotheses and not being easy to work with, basically. And so there are a lot of papers and scientists that argue that it is fundamentally the lack of a theory for life that leads to a lack of a satisfactory definition, and that ultimately prevents us from making conceptual progress in biosignature science. And I disagree. Oh, well, okay. Surely proposing proposing new ideas for a universal theory for life certainly strengthens the field, but I think the extent to which it drives it deserves to be nuanced. So for example, if we look at origin of life studies, I think we have a lot to learn from them, because they teach us that we do not need a perfect definition or a perfect theory for life to arrive at very compelling theory for the emergence and the origin of life. So for example, the hydrothermal vent hypothesis or the primordial soup. We can debate about these ideas, but these are compelling ideas that are very complex and very content heavy, that did not require a perfect theory for life. Okay, so then another question is, are biosignatures in our way? So you might have noticed that I have avoided so far giving you a proper definition of biosignatures, and this is because within the literature, I noticed that not only are we unsure about what we talk about, so life in general, but also how we talk about it. So let's dive into that. So the most used definition for a biosignature was written by Demara and Welter in 1999. and defines a biosignature as an object, substance, or pattern whose origin specifically requires a biological agent. Now, this definition actually leaves room for a lot of confusion between the measured signal, the inferred presence of the species in the atmosphere, and the interpretation and the conclusion that life is or is not present. And actually, I had a lot of fun noting down all of the ways that different papers describe or define their biosignatures or what they mean by it. So, for example, in one paper, you might have a biosignature that is a signal suggesting the presence of life. In another, it's a signal that is consistent with life. So does that mean that we do not wait for a biosignature or a signal to be disentangled from false positives before calling it a biosignature? So therefore, it doesn't actually require per se a biological agent. Also, does a biosignature need to be detectable by definition? If this is the case, does this mean that its meaning will evolve as future instrumentation improves? And then in recent years, you also have you've also had the appearance of this field called agnostic biosignatures, which are supposedly biosignatures that do not presuppose any underlying biochemistry, so are meant to also apply to life as we don't know it. But does that mean that biosignature in itself only applies to life on Earth? So how trustworthy is the word, basically? Also, I see that a lot in many papers, the expression strong biosignature gas. So does that mean that you can have a weak biosignature gas? So that means that we're not too sure that life is involved. And also with the advent of quantitative frameworks, what are the thresholds within the statistics and within these probabilities that we involve beyond which we can invoke life? So it's oh, and I forgot, yeah. And I think it's 2 years ago or 3 years ago now, you now have words that are making their way in the literature, such as a biosignature or anti-biosignature, which are supposed to be the opposite of biosignature. But then you end up at the same issues with defining them and knowing exactly what they refer to. So it's a big mess. And there's obviously a huge lack of community standards when it comes to what we mean by a biosignature. And it leads to scientists expecting and discussing in their papers different pieces of evidence for the same problem and vice versa. And in my opinion, it's really a quick fix that actually never gets fixed. So I think that we need a consensus on a semantic framework, and we need to settle down on what we mean by a biosignature, and any other expression that we choose to distinguish it from. This is way easier to do than agreeing on the universal theory for life, but I think that it will definitely strengthen the field and improve a lot the discussions. Okay, so actually, above all, what seems to drive and hinder when they're not present enough intense advancements in biosignature science are the multiple interdisciplinary collaborations that need to happen for astrobiology to thrive, and how well connected this network is. So, if we look at exoplanet biosignatures, well, it requires the contribution from mathematics. So, for example, Bayesian frameworks is basically pure maths. Philosophy as well. So, for example, understanding the difference between life and living, or having a very clear understanding dynamic between theory, definition, and observation. Physics, obviously, to understand the physics of life in general. Also chemistry, so obviously when it comes to disequilibrium, understanding redox chemistry, but also atmospheric chemistry, photochemistry, prebiotic chemistry. Climatology, so that is the impact of clouds on spectra, for example, or the feedbacks between the atmosphere and the ocean, and the different elemental cycles. Astronomy, obviously, with everything related to the remote observations of these planets, the line list, the spectral features that we observe. Geology with, nitrogen cycle, like oxygen, water cycle, and tectonics, for example. And finally, biology, obviously, with, understanding ecology, understanding population dynamics, understanding metabolism, and the origin and emergence of life, etc. So, all these fields need to be very well connected in order to work well together. But not only these fields, but also the different actors within them. So, observers first, and empirical or lab scientists that provide the ab initio data about all the elements, for example, theorists as well, and obviously modelers. And you would actually be surprised as to how few studies intersect between these different actors. And then, I really want to emphasize as well how unexpected high potential interdisciplinarity can be. So first, I put here in situ biosignatures and technosignatures. So I put them in a different kind of bubble because they don't interact that much. It's quite unexpected, actually, but they're very different and they use very different techniques. However, in situ biosignatures have a lot more room for innovation because they can literally go to the place they're investigating. They also have a lot more experience with false positives, and they produce more readily testable hypotheses. And there's a general trend of trying to adapt in situ biosignatures to exoplanet biosignatures. And then I also put technosignatures here. So I don't know how familiar you are with the field, but these are, people that are usually very creative about how they approach a problem. And also, I think there's a lot of potential in trying to combine exoplanet biosignatures and technosignatures. So, for example, there was a paper on like nitrous oxide as both a techno and a biosignature, which I found very interesting. And finally, it can come from very unexpected areas. So I think we have a lot to learn from industry, and especially, if I give you an example, industry has come up with a lot of very efficient ways to classify chemical species from a very small subset of the properties. They also have very efficient ways of handling and managing a large amount of data. So for example, the pharmaceutical industry or the petroleum industry. So I think these are definitely collaborations that we need to seek out. Okay, so interdisciplinarity is not very straightforward, and you end up with a very complex feedback web or interdisciplinary network. And what you need are, connections that need to be established between all these different fields and actors. You need these interactions to be saturated and the feedbacks to go both ways. So in my opinion, an example of a feedback that doesn't really go both ways is innovative concepts driving new observation techniques as much as existing or scheduled instruments driving new studies. And I think this feedback should really, especially the former one, should really become stronger. Otherwise, we end up being conceptually lazy, which we don't want. In particular, I think there are two interdisciplinary routes that I would like to emphasize with you. And the first one relates to distancing ourselves from astrobiology per se and look at the plentiful insights that abiotic studies provide. So, for example, our understanding of habitability and biosignatures relies on our ability to accurately model both inhabited and uninhabited, and habitable and uninhabitable worlds. Second, well, if you remember the Bayesian framework, it relies a lot on accurately constraining the probability of a signal arising given the absence of life. So that's something that we also need to constrain and learn to approach. Also, whether we're talking about the concentrations of a gas in an atmosphere or newly emerging work on quantifying complexity, all this relies on the correct estimation of thresholds, which are based on a good understanding of what biology is and does, but also of what we consider to be abiotic. And finally, it is very important to realize that a lot of technological and methodological advancement is often made by characterizing hotter and larger planets first, for which we have more data and it is more readily available. And larger planets are also very important when it comes to planetary formation, informing planetary system dynamics, and for example, water delivery. So they're not totally out of the question when it comes to habitability. And finally, the second route is to keep pace, and especially astrophysics needs to keep pace with the lessons that we learn from Earth. So in the same way that biology has evolved from a complex eukaryotic-centered perspective on life on Earth to recognizing the prevalence and tenacity of prokaryotic life, we shouldn't lose sight of this aspect in astrobiology. Also, as a lot of scientists work on extremophiles today, these studies expand the known parameter space of life on Earth. So here is, for example, a plot of where we have found organisms in terms of pH, temperature, and salinity, which I find is a super cool plot, a bit outdated now. But we should really stay updated on this kind of parameter space for life, at least on Earth. And finally, we shouldn't decouple our search for life in the universe from origin of life studies. So we're looking for inhabited worlds, but we're also looking for places where life can originate and can emerge. And for example, a lot of study in this area in the recent years has consisted in mapping environments in terms of electron donors and acceptors, which so far hasn't really been done in astrobiology. And then finally, it's also important to keep in mind what the early exploration of our solar system was. Why? Because near future space missions are going to provide a very similar resolution. So for those who are familiar with resolution values, so resolution less than 100, so very similar resolution to the early stages of disk integrated spectral investigation of our solar system. So we have a lot of insights to draw from that evolution in history. Okay, I'm almost done. So I really want to emphasize here and bring everything together to show you that the nature of biosignature science ultimately is a fundamentally iterative effort and a very complex feedback web. So I want to highlight 4 different iterative loops, which in my opinion are kind of the pillars of biosignature science that we need to work on. The first iterative loop relates to extrapolation conditions. So the processes that as in the investigation scenery where we extrapolate our known biological processes. And this loop, this iteration is advanced by both looking inward and outwards. So outwards, that was our story of horizon extension. So how our scenery went from being the solar system, Mars first, then the solar system, and then exoplanets, and then the different exoplanetary environments within these planets, and especially atmospheres, and inwards with learning and knowing more about the behavior and the evolution of our planet. And this iteration is actually quite well illustrated by the evolution of our modeling benchmarks. So we went from only using the modern Earth as our modeling benchmark to using the early Earth, so the Archean Earth, for example. And I've actually recently participated in a whole new intercomparison benchmark, which was based on TRAPPIST-1e. So a famous exoplanet that you might know that is in the terrestrial habitable zone of its star. So that's very interesting and definitely going forward. The second iteration relates to the biological processes that we extrapolate in this scenery that I described above. And it's actually very interesting to see that in the literature over 40 years or so, we went from only considering life as we know it and very Earth-centric biosignatures to actually completely discrediting it with the advent of biosignatures by saying, oh, but it's only one sample point, it doesn't mean anything. We should look for life as we don't know it. And then in more recent papers, you have this idea that actually the diverse metabolic abilities and lineages that we find on Earth, coupled to the varied environmental states that they're found in over geological timescales, actually map life on Earth to a sample size superior to 1. The third loop relates to what I call loop ideas. I don't really know how to call it another way, which illustrates the cycling shift between new ideas and feasibility, which is often linked to instrument capabilities and method prioritization. So for example, a newcomer in the field might see that recently there has been a lot of papers on exoplanet maps of terrestrial exoplanets as the new surface biosignature to really focus on. But actually, this is an old idea that dates back to the 70s, and that kind of resurfaces every 10 years or so in a different context. So it started with the first light curve inversions of solar system objects in the 70s. And then you had the first map of a hot Jupiter planet, to today, considering these first terrestrial maps as new biosignature concepts. Perhaps a more famous example relates to the direct imaging of exoplanets and interferometry. So, having the idea of having an interferometer in space to detect life on other planets dates back to the 1990s. And, you might remember that in the early 2000s, we had the NASA project Terrestrial Planet Finder, the ESA project Darwin mission, to have this space interferometers. Both of these projects were abandoned in 2007 due to technological limitations. But as ground telescopes now are pushing the technology forward, you can actually see in recent papers in the last year or so, this idea kind of resurfacing and saying that this is now the time to do it as something totally new and innovative. So it's very interesting, and in my opinion, to see this kind of cycling of ideas every decade or so. And then finally, the kind of all-encompassing iteration is what is similar to chicken and egg problem, where searching for life improves our understanding of life, and better understanding life improves our search for life. And you kind of have the same feedback with biosignatures, where searching for biosignatures leads to new biosignature concepts, and new biosignature concepts to a better search and a better understanding of biosignatures. And this is also illustrated in the Bayesian framework, where you kind of update your knowledge as you observe new planets and you accumulate data. But I think a very powerful and optimistic realization is that ultimately, this is an empirical problem with testable predictions and observables, which is why exoplanet biosignatures are so critical in our understanding for life in the universe. And I guess the challenge is just to make these 4 iteration loops co-evolve as tightly as possible, and make sure that they're as connected and as what I call temporally tightened as possible, so that we have the least catching up to do between each field and each iteration. Okay, so onto the conclusions. I actually have very general conclusions, because you might not be experts in exoplanet biosignature science, but I think that these are conclusions that you can apply to literally everything. So I think the main idea is that looking at the time-integrated and interdisciplinary picture of a field in general, whether biosignature science or not, is extremely insightful. First, it highlights the evolutionary trends of the field. Second, it puts in perspective any new idea or discovery by saying, is that innovative, is that new, or can I draw insights from this in another context? It also allows to spot truly innovative ideas, as I just said, and ways forward. And finally, it questions our priorities, and in my opinion, it really enhances the need for more communication, more collaboration, and more intercomparison between our different methods and strategies. And I don't think that we've been stuck with the same concept for 50 years because we lack the answers. I think that a lot of answers are out there, but what we lack are the connections between different fields that can build this answer together. And by the way, this talk is not on the legitimacy of disequilibrium chemistry. It's a great concept, but I'm just saying that, you know, relying on only one concept is a risky life. And I'll end with this. So I haven't put many references in this talk, but you can find all of this hopefully well written down in this article that was published in December 2021 in A&G. So if you just want to have a look at the references, you'll find a lot of the ideas and there's justifications of everything that I said, so that you know that it doesn't come from nothing. But yeah, thank you for listening, and I'll take any question.
Okay, thanks very much, Estelle. And if people have got questions, if they can either do it through the chat or just raise their electronic hand, then it will allow me to see. I can see a hand in the air there from Chris Hooker. Your microphone's not on, Chris.
I was actually applauding rather than raising a hand.
Oh.
Thank you very much.
You're welcome.
No problem with that.
Can I ask a question?
Brian.
Thank you, Estelle, for a very erudite talk. Thank you. So you were talking about a new horizon in our understanding in 2030. Is that driven by the James Webb Space Telescope, do you think?
Oh, that's a controversial question.
I didn't think it would be controversial.
So yes, definitely James Webb is going to contribute a lot in terms of, you know, bringing new insights in the kind of atmospheres that are out there. Also, the telescope that is going to be launched in 2028 called Ariel. I might be biased because Giovanna is the PI of that, so maybe don't take me as objective. But I think these two telescopes together are definitely going to bring a lot of insights. Ground telescopes as well, so the ELTs are coming. Where I would nuance the contribution of James Webb is that in terms of terrestrial planets and astrobiology, you know, the performance is not really there. You're going to be able to see like your CO2 signal at 5 sigma in this terrestrial planet, but that's about all. And then once you have clouds, your spectrum just becomes totally flat. So
that's a bit disappointing. Spent all this money and all this waiting.
Yes, it's because, you know, James Webb it's been there for 30 years and people have tried to adapt it to literally every field possible. Understood. So it's not optimal for any of it, but it's definitely going to contribute. It's definitely going to bring a lot. But I would nuance it for astrobiology, definitely. But in exoplanet science, it's going to be brilliant.
Yeah, sure. Thank you very much.
Alan W.
Yes, you mentioned the Bayesian approach to this, which basically means you're making a lot of measurements and going to evolve probabilities therefrom. One of the things it depends to some extent on, although not greatly, of course, is the initial probability. For example, are there cows on Mars? Well, don't know anything else, 50-50. So you start there, or you might say, well, it's got to have grass as well on Mars, so maybe less than 50-50. So there's that initial thought about what goes into that initial probability. You've now been doing, I assume, over the last 50 years or so, you and others, getting lots of data to feed into that likelihood function. I'm just wondering whether you've now got a best guess at the moment for what the probability is that there's life out there in the universe based on this Bayesian equation.
Okay, so that's a very good question. The answer is that you might think that we've accumulated a lot of data in the last 50 years, but that's not the case. You know, Kepler was in 2010. It basically just gave statistics about the nature of planets. We don't have data about exoplanetary environments yet. So our likelihoods are very poorly constrained. About our priors, the goal is to have as many fields contribute to that prior as possible. But so far, collaboration is not strong enough that our prior is very well constrained and very well updated either. So far, our Bayesian framework is actually working very well in pure exoplanet science, but for astrobiology, we're not there yet. So we don't have a clear posterior probability of life.
Do you have a timescale in which you'll be able to start applying that equation, do you think?
I would say after the third horizon extension, so by 2030. Definitely, yeah. But then what we can do, though, is to try to anticipate kind of this diversity of exoplanetary environments and build that posterior probability from models of exoplanet population studies, which is being done. And but we'll only be able to compare that and actually assess its correctness once we have more data, and especially more astrobiology relevant data.
So you're not going to be able to give me too much of an answer about whether there's cows on Mars?
I know this is too political for me.
There's a lot of methane, there's a lot of cows.
Methane's a powerful biosignature for that reason.
Thank you.
I think it's 26.34%.
That's a good number.
Minus the natural log. Chris H.
Yeah, Estelle, thanks for a really interesting talk. You talked a lot about the sort of probabilistic aspects of how you might identify whether there's something there. In some areas of science, at least, there are what they call golden results, like there's something which definitively proves there must be something. I mean, as an example, the thing I'm thinking about, when the positron was discovered, it was discovered in a cloud chamber, and it was a track that spiraled in the opposite direction, which proved it had to be the opposite charge. Is there anything like that in astrobiology that could unequivocally just say, if you see it, yes, that must mean some form of life?
That's a great question. And actually, if you see papers around between 2000 and 2015, I would say, all the astrobiology papers are about smoking guns. So what you call golden targets, which are basically you detect a signal and you can say there's a biosphere there, 99.999%. What the realization has been in the last few years is that such smoking gun doesn't exist. So you can work with confidence levels, you can work with probabilities, but ultimately you'll have to assess not only a signal but your star. What its activity is like. What do you have clouds on your planet? Do you have planets around it? What the interstellar medium looks like? Does it have asteroids? It's kind of an integration of the whole situation together that might gonna tell you your confidence level is high enough for you to assume that it's life. The only problem with astrobiology is that ultimately we'll never know, like we can arrive at a 99% confidence level and it might be something that we totally missed, and that it's just we just don't understand the process. It's not the same laws, it's not the same it's not the same laws, it's the laws of physics, but it's just not the same environment, and it's so different that we cannot even model it and compare it with our models. But if such kind of equivalent or as close as we can to a smoking gun exists, it would be the integration of a planet, stellar host, and signal integrated together, if that makes sense.
Okay, thanks.
Estelle.
Can I ask one, George?
Oh, I was just going to ask one. Go on.
Sorry. Go on after
I'll
you.
share rank on you, and then you're next, Pauline.
Okay.
And it's the obvious controversial one. Did we learn many lessons from the phosphine on Venus?
Oh, George, that was my question. Saves me bothering.
Okay, so again, I'm going to warn about biases here because I was very upset with this paper at first, and this mainly has to do with science communication and the way they kind of jumped on the prospect of calling it life straight away. They called their press release "Hint for Life on Venus," which I think wasn't very scientifically professional. But apart from this, it's always very interesting to detect a molecule in an atmosphere that we cannot explain. That being said, Venus is our neighbor. It's extremely similar to the Earth in terms of planetary parameters, yet we do not understand its atmosphere. Its photochemistry, so the way light interacts with its high sulfuric clouds, is not understood. We don't know what's happening out there. So claiming that it could possibly be life when we cannot even understand how its atmosphere is interacting with the different molecules is a very bold statement. So if anything, I think that the main lesson that we learned is that it's obviously claiming like the biosignature is there, claiming that life is there, attracts a lot of popular media attention, and this is good for the field, but it also hurts it a lot, because then we're going to be taken less seriously when we actually have more evidence and more confidence for it. But in terms of science, it triggered more missions on Venus, which is always something that we want. It triggered more interest. It's going to trigger more studies. It's going to trigger more studies also for phosphine, which is not a very well-studied gas. You know, it's basically led by Clara Souza Silva, who is the only person who's been working on phosphine. So it's always good, you know, but I would nuance it a little bit.
How many biosignatures could be misinterpreted?
Every biоsignature can be misinterpreted, but again, it depends on what you call a biоsignature. So if you call it a biоsignature before it's disentangled from false positives, you don't have a risk of misinterpretation. But then what are you going to call your signal once you're very, very confident that it's life? And then what are the misinterpretation risks associated with that? So it really differs on the words that you choose here, but anything can be misinterpreted, like basically. And if anything, we're literally we're realizing more and more that exoplanets constitute so much more diverse environments than we had expected, that force us to account for more and more parameters and more data and let's say like circumstantial considerations.
Thank you.
Brian.
Estelle, I suppose the position is strengthened if life, if it's completely hypothetical, but if life always took effectively a similar route to us, then your position is obviously much stronger if that were the case. And I remember Sarah Seeger commenting that you would build, in order to determine whether there were likely to be life around a given planet or a planetary type, that you would have to sort of edge towards the probability of there being from many, many planets. But that will only be true really if there is a limited number of ways in which life can evolve. And if life has a huge variety of ways of evolving, and there are a huge variety of gases that life can produce, then that obviously makes it much more difficult to be definitive about whether you have in fact detected life.
Absolutely. And this actually depends upon how chemically dependent you are on the way you understand life. So far, our understanding of life is depending on its byproducts. So, you know, oxygen is a byproduct of photosynthesis. But let's imagine a totally different chemical environment. Can you expect totally different byproducts? And then you have a risk of you know, not getting there very quickly.
Yes, precisely.
And actually, there's a lot of work, not a lot of work, but someone called Sarah Wolke, who I absolutely love and I'm fascinated about, who works at Arizona State University on quantified complexity. So approaching a planet and its atmosphere in terms of a network of everything that is happening in this planet, including a possible biosphere. So then this leads to considerations that are more biochemistry independent, but more related to the topology of your network in the end, which I think is very interesting.
But presumably that requires detection of the other areas in that diagram where you showed not just gases, but the other aspects, you know, the red edge and the variability, the curve that you showed. It presumably requires a much more technologically sophisticated set of observations.
Yeah, we're not there yet.
No, but that's great. It's a very good point. If you can, yes, of course, if you have other modes of detection, other things that you can detect, that you're less. I think we will probably have to be, but I think we will just have to keep trying, because and undoubtedly we will keep trying because it's so fascinating.
Yeah, it is.
But,
And
yeah,
actually, I would argue that even if we don't find it, the astrobiology and biosignature in itself has so many advantages in terms of the people that it brings together, in terms of all the
Absolutely.
scientific insights that it produces, with or without a positive detection.
Yes, I mean, we'll learn so much, and we will be taken by surprise, no doubt, by James Webb and Ariel and so on. So I think it's absolutely fabulous. We should never, I don't think we will ever give up. There will always be people who want to keep going. And
Absolutely.
Whether we actually get the yes or no definite, well, we'll never get a no, but whether we, even if we don't get a yes for centuries, you know, the journey will be fabulous.
Yeah.
Jay, you're muted. All right.
Yeah, thank you, George. Estelle, thank you. First of all, that was quite interesting. I remember reading about exoplanets around Proxima Centauri. What do you think of that? What are the chances of biosignatures around that? Has there been any more advancement on that stage?
Okay, so so Proxima Centauri b, which is one of the closest exoplanets to us, and is very interesting for that indeed, and also has been shown to orbit in the habitable zone of its host star. So, you know, even more interesting. The only problem with this planet is that it's not transiting. So the way it orbits around its star means that it never passes between us as observers and the star. So we never see it transit in front of its star. And transit spectroscopy is basically the way today that we have to probe the atmosphere and therefore search for biosignatures. So if you don't have a transit, it's a bit hard to draw conclusions. There is an interesting paper by someone called Bergina, who has been talking about exoplanet maps on Proxima Centauri b by analyzing the thermal emission of the planet. So it doesn't need to transit then, and you would just get the light that is emitted by the planet. But, you know, again, this is a bit not, I mean, it's not very relevant to current observatories. So I think even though it's a very interesting planet, we'll have to wait a bit to be able to observe it and probe it for astrobiology. Unfortunately, it's honestly, it's such a shame because it's so close, but it's not transiting.
Yeah, exactly that. I was thinking it would be so much easier if we found something there.
Yeah, but it's an issue.
We'll have to send a little robot spacecraft to the system.
That would be great. They'll have to do it soon for me to send it to see it before the end of my life. But
Oh,
you know,
well, if it's too late for you, it's definitely too late for me.
It's only 4 or 5 light years away.
But, you know, you never know what tomorrow's technology will bring.
Okay,
Yeah,
I know Estelle was keen because she has to move on. So can I just say, firstly, thanks very much for a very stimulating presentation. It must be fantastic to be at, in effect, the ground floor of this branch of science, as opposed to working on, say, physics or chemistry, which has been going for hundreds of years. And try not to get too bogged down by definitions, because I get the feeling, well, certainly scientists can go round and round in spirals, trying to define even smaller and smaller things, and thereby ignoring going out and getting the big data. So once again, Estelle, thanks very much for a great talk.
Thank you very much. Pleasure for me to be here. Again, don't hesitate to email me if anything. I'm not at this stage where I get overwhelmed by emails and I can't reply. So, you know.
What is your email address then?
Oh, I'll put it in the chat.
Yeah. Okay. Are you going to do a PhD, by the way?
Yes, I am, with Sarah Walker.
Oh, wow. Your favorite astrobiologist. Brilliant.
I'm going to go live in a desert.
I think my company did a study with your supervisor, because I work for SSTL, which builds satellites, and we did a study for an exoplanet spacecraft called Twinkle. But I don't think
yes, Joanna's the PI of that. Yeah,
yes, exactly. Yeah, but it's not a real spacecraft, I don't think. I think it's still a study. But I know people who were involved. I wasn't involved.
It's very interesting. It shows, you know, the prolific interactions that can happen when you also involve private companies, and you know, you don't get strangled by slow public
Yeah,
funding.
because they're very slow. We're ridiculously quick. We sign up to
Yes.
do emissions in just over a year.
Exactly.
It's crazy. This is why I'm always shattered.
Yeah. Okay, I need to head off, but thank you very much again, and yeah, see you. I don't know when.
Thank you very much, Estelle.
Bye.
Yeah.
Have a good evening.
Bye.
Bye.
Thank you, Estelle.
Bye.
Okay, just a couple of quick announcements, then we can have a wee break. First one is, I guess on a bright note, we are going to be going to the Bright Walton Mayfair, which surprisingly is on the 1st of May. So please do come along and visit and say hello. So that's that bit. Because there are so many of you, I'm assuming nobody went to the St. Francis tonight, because the old venue has gone because they wouldn't allow us to have internet. So we've got our new venue, and all the details will be on the webpage, including the map. The only issue, I think, is car parking, and thanks to the efforts of Kath, we've got lots of car parking space, one at the church hall, well done, Kath, one at the garage just up the way, and then whatever parking space you can get actually at the event hall itself. And we've got something like 5 or 6 car parking spaces at the back of the hall as well. So that should be okay. And we'll have obviously the April meeting will be there. On less good news, some of you may know someone called Andrew Collier, and I know him because we worked at the same place. Had a problem with his heart. He went to hospital. They've said there's no treatment they can do, so they were just going to make him comfortable in hospital. I got an email from his daughter this evening saying that he seems to have had what I'll call a minor recovery. His condition is not treatable, so he'll be at home as of Monday. So it's sort of bright news. I'll email her again and ask if he's okay with visitors, and then go round and give him people's regards. So it's where are we at? 1:45. So we can have a break till 9 o'clock. If anyone has any talks or things they want to discuss, they could let me know over the break time. But when we come back, I'm going to do a very quick overview of some astronomy software that's quite cheap and extraordinarily powerful, and then do probably the quite silly thing of giving you a live demo of it. So if it doesn't work, it's the computer's fault, because it's never mine. The operator is absolutely perfect, but hopefully it'll give you a taste of what can be done. And then I'll finish by showing you 5 or 6 of my latest images using that software, so you can see what it's actually done as far as the images. The good news is, assuming the computer works, in 10 or 15 minutes, we'll have more or less a finished image, which I think is not a testament to me, it's a testament to the software. I'll leave the thing running, I'll turn the recording off, and that will go up on the Newbury Astro YouTube channel. So the screen is yours, and